Now that you have an understanding of how segments can be created with cluster analysis, the next step is to analyze them to see how they differ from each other. If you recall, in cluster analysis, there is no statistical test involved. You are simply creating clusters based on their dissimilarity from each other. But if you have a small sample, any dissimilarity may be illusory, that is, due to sampling error. The only way to be sure that the segments are indeed different is by conducting a statistical test. That is the topic for discussion in this and the next few modules. Our objective here is to understand how segments differ from each other so as to formulate a marketing mix that will appeal to them. There are many ways in which segments could differ in ways that would be important to marketers. For example, how do they differ in the importance they attach to various product attributes or to price? That would be important in developing a positioning for our products. Do they differ in how much they buy or consume of certain products or brands? Do they differ in what shows they watch or magazines they read or radio stations they listen to? How does the profile of heavy users of the product category differ from light users? When we want to compare segments, the type of analysis or test we conduct will depend on a couple of factors. First, is the dependent variable, that is what we are comparing the segments on, quantitative or categorical? Second, how many segments do we want to compare? If the variable is quantitative, for example, if we want to compare ratings on a scale or dollar expenditure or purchase quantity across the segments, then we can use a two-sample test of means or ANOVA if we have two segments. If we have more than two segments, then ANOVA is the only option. If the variable is categorical, for example, whether the buyer purchased a particular brand or shopped in a particular type of store, or whether the product was on promotion, then we can run a cross-tabulation, or crosstab for short, regardless of how many segments we have. If we have two segments, we can also run a two-sample test of proportions. However, we will not be covering this test here, as a crosstab can be used instead and will give the same results. Let's take a deep dive into how to conduct a statistical test for a crosstab. The statistical test with a crosstab is a chi-square test of independence. This is basically a goodness of fit test. That is, it is used whenever you want to see how well an observed frequency distribution fits some hypothesis about the population. We can use this to test whether the segments are the same on some categorical variable or whether two categorical variables are independent of each other. These two statements are equivalent. That is, if there is no difference between the segments, the segmentation variable is unrelated to the other variable. So our H0 is that the variables are independent. The alternative is that they are not independent. We use a chi-square test statistic, pronounced chi-square. The basic idea here is that if the variables were independent, we'd expect to see a certain frequency distribution in the table. This is based on the probability of independent events, which says that if two events, A and B, are independent, then the probability that they occur together is the probability of A occurring times the probability of B occurring. Based on this theory, we can calculate the frequency distribution we would expect to see, that is, the expected frequency, and compare it with what we actually see, that is, the observed frequency. Let's take a quick look at the logic for calculating expected frequency. Suppose we defined two events as 1, whether someone is under 30 years old or 30 and over, and 2, whether they like Starbucks. We want to calculate the expected frequency if the two are independent. That is, liking for Starbucks does not depend on their age. Here's what a crosstab of the two variables might look like. The columns represent liking for Starbucks and the rows represent the age groups. The row totals show the number of people in each age group, 100 and 300, and the column totals show the number of people in the like and don't like groups, 200 and 200. We start by calculating the probability of each group in the sample. There are two groups based on the rows, that is under 30 and 30 and over, and two groups based on the columns, that is like Starbucks and does not like Starbucks. We need to calculate the probability of each group. How do we do that? Well, that's easy. It's just the number of people in each group divided by the grand total, which is 400. So, if we randomly chose a person from this sample, the chances that they would be under 30 is simply 100 over 400 or 0.25. That's the probability of being in that group. Similarly, the probability of being 30 and over is 300 over 400 or 0.75. Using the same logic, you can calculate the probability of people liking and not liking Starbucks. Now let's see how we can use these probabilities to calculate the expected frequency in each cell in the crosstab. Consider the groups age under 30 and likes Starbucks, yes. What is the probability that they occur together, as in the top left cell? We start with the probabilities we just calculated. Remember that the probability of two events occurring together is the product of their individual probabilities if the two events are independent. So the probability of being under 30 and liking Starbucks equals the probability of being under 30 times the probability of liking Starbucks, which is 0.25 times 0.5 or 0.125. In a sample of 400 people, we would expect to see 0.125 times 400 or 50 people in the top left cell. That's the expected frequency for that cell. We can calculate the expected frequency for each cell in a similar way. Notice that the total of the expected frequency in each row or column always equals the total we observe in that row or column. That's because the probability of being in each group is always the same as what we observe, but the distribution of frequency across the cells changes based on the assumption of independent events. If you work it out, the formula for calculating expected frequency simplifies to row total times the column total divided by the grand total. Do you remember this example? We looked at it a while ago to understand how to interpret a crosstab, but at that time we did not conduct a statistical test. The two segments we are comparing here are Samsung owners and non-owners. Let's ask the same question. Was there a difference between Samsung owners and non-owners in their usage of the coupon? To understand what the data mean, we looked at the proportion of Samsung owners that use the coupon compared to non-owners. We found that 150 out of 450 owners used the coupon compared to 100 out of 150 non-owners. So our tentative conclusion at the time was that the coupon attracted non-Samsung owners more than Samsung owners. But this could have been due to sampling error, and a different sample might have found no difference between owners and non-owners. So we need to conduct a statistical test to determine if this result is significant. We will now conduct a chi-square test to determine if we can reject the hypothesis of independence. First, we calculate the expected frequency in each cell. This equals the row total for that cell times the column total for that cell divided by the grand total. For example, the expected frequency for the cell 1, 1, that is in row 1, column 1, is calculated as 150, which is the total for row 1, times 250, which is the total for column 1, divided by 600, which is the grand total. This gives you an expected frequency of 62.5. You can similarly calculate the expected frequency for cell 1, 2, that is row 1, column 2, as 150 times 350 divided by 600, which gives you a value of 87.5, and so on for each of the four cells. Now we can use Excel to conduct the test. First, we calculate the expected frequencies, as you saw, and put them in a new table. Here, for simplicity, I've shown them in red in the same table as the observed frequencies, but you need to put them in a new table for Excel. Then we use the function chi-square.test to get the p-value. Remember that the p-value tells us whether to reject the null hypothesis or not. Our decision rule is, if the p-value is less than 0.05, we reject the null hypothesis, and if it is greater than 0.05, we do not reject it. So now we'll take this into Excel. Here's how to set it up. You have the original crosstab on top with the observed frequencies. Then you create a new table and enter the expected frequencies there. In the last step, you use the Excel function chi-square.test and enter the range for the observed, then a comma, and then the range for the expected frequency. Here the p-value is so small that Excel writes it in scientific notation. E to the minus 13 means that the first number, 7, is in the 13th place after the decimal point. Based on this, should we reject H0? The answer should be obvious. Since the p-value is less than 0.05, we should reject the H0 and conclude that the two variables are not independent. That is, the segments are indeed different. So now, what can we say about the difference between the two segments, Samsung owners and non-owners? Clearly, there is a difference. We can now confidently say that the coupon was more likely to attract non-Samsung owners.